Let me start with something that ought to bother you, even if you've never thought about it before. Take a deep breath. Now look around you. Everything you see, the chair, the screen, your hands, the air filling your lungs, is made out of atoms. That's the part everyone tells you. But here's the part they usually skip over because it's uncomfortable. Atoms should not exist. I don't mean they're unlikely or they're mysterious. I mean that if you take the basic rules you learn early on and push them just a little, atoms have no right to be stable at all. They should collapse or fly apart or smear themselves into nothing. And yet here they are, stubbornly holding together, building stars, rocks, cats, and people who sit around asking questions about atoms. So the question isn't what are atoms made of? The real question is why haven't they fallen apart? Now imagine, just for a moment, that you're very small. Not metaphorically small, I mean really small. So small that an atom looks like a cathedral. In the center there's a tiny dense nucleus, and far away there's an electron, and between them, almost nothing. Mostly empty space. That's already strange, but let's accept it for now. The electron is negatively charged. The nucleus is positively charged. They attract each other. Everyone knows that opposite charges attract. Fine. So what should happen? The electron should fall straight into the nucleus. Bang! End of atom. And if you're thinking, well, maybe it just goes around in a nice circle like a planet around the sun, that's exactly what people thought at first. And it's exactly where the trouble begins. Because according to classical physics, a charged particle that goes in a circle is accelerating, and an accelerating charge radiates energy. It leaks energy like a car with a hole in the gas tank. So the electron orbiting the nucleus would lose energy. As it loses energy, it would spiral inward, faster and faster, tighter and tighter, radiating energy all the way down until zap, it crashes into the nucleus. The whole thing would take a tiny fraction of a second. If that were true, every atom in the universe would self-destruct almost instantly. No chemistry, no solids, no light, no life, no you. And yet here you are, staring at a screen made of atoms that clearly didn't get the memo. This is the paradox. Atoms are made of parts that, by all the usual rules, shouldn't stay put. And yet they do. Not just for a moment, but for billions of years. Hydrogen atoms formed shortly after the universe began are still around today, minding their own business. So what's holding them up? You might think the answer is some kind of glue. A force we forgot to mention. A tiny atomic superglue that keeps electrons from crashing in. But that idea doesn't work, because any ordinary force you invent just brings you back to the same problem. Force means acceleration. Acceleration means radiation. Radiation means energy loss. And energy loss means collapse. It's like trying to fix a leaky boat by drilling more holes. Now here's where the story gets really interesting, because the solution to this problem didn't come from adding something. It came from taking something away. Specifically, taking away the idea that an electron is a little ball doing whatever it pleases whenever it pleases. Nature, it turns out, is far pickier than that. Before we get there, though, let me tell you a little story, because stories are often better than equations. Imagine you're standing in a room with a violin string stretched across it. You pluck the string. It vibrates, but it doesn't vibrate in just any old way. Only certain patterns are allowed. Certain standing waves fit on the string, others don't. You can't have half a wave plus a tiny extra wiggle. The string refuses. It either fits neatly or it doesn't exist at all. Now imagine shrinking that violin string until it's unimaginably small and curling it around a nucleus. The electron, instead of being a tiny planet, starts behaving like a vibration, a pattern. A standing wave, and here's the remarkable thing, only certain vibrations are allowed, not because we say so. Because the universe says so, this is not a matter of convenience or ignorance. It's a hard rule. The electron cannot have just any energy it wants. It can only have specific energies. If it doesn't fit, it doesn't exist in that form. And this one idea changes everything, because if the electron can only exist in certain states, then there's a lowest one, a ground state. A state where the electron has the least possible energy it is allowed to have, and once it's there it cannot radiate away any more energy, not because it's tired, not because it's stuck, but because there is nowhere lower to go. This is the key. This is the escape hatch from collapse. In classical physics, you can always lose a little more energy. There's always a slightly lower orbit, a slightly tighter spiral, but in the real atomic world there is a bottom, a hard floor. And when the electron reaches it, the rules simply do not permit further collapse. That's why atoms exist. Now I want you to notice something subtle here. We didn't say the electron knows it shouldn't fall in. We didn't say it's being pushed away by a magical force. We said that the very concept of what the electron is has changed. It is not a marble rolling on a track. It is a quantum object, which means its behavior is constrained in a way that has no classical analogy. And if that makes you uncomfortable, good, it should, because this isn't just a fix for atoms. It's a statement about reality itself. It says that at the most fundamental level, nature does not allow arbitrary behavior. It allows only certain possibilities. And the rest are not just unlikely, they are forbidden. Now here's another twist that people often miss. Even in this lowest energy state, the electron is not sitting still. It cannot sit still. If it did, we'd know exactly where it was and exactly how fast it was moving. And the universe doesn't allow that either. There is a built-in fuzziness, a restlessness, a kind of unavoidable jitter. The electron must have some motion, some spread, simply to exist at all. If you try to pin it down too tightly, you give it too much energy, and it pushes back by spreading out. So the atom is stable not because everything is calm and frozen, but because everything is in a kind of dynamic balance. A perpetual dance where collapse and explosion are both forbidden by deeper rules. This is already strange enough, but now I want to make it personal, because this isn't just about atoms in textbooks or diagrams. This is about you. Your body is made of atoms that exist only because the universe enforces these quantum rules with absolute rigidity. If those rules were even slightly different, chemistry would fail. Molecules wouldn't form. Proteins wouldn't fold. Cells wouldn't function. You are not just made of atoms. You are made of the fact that atoms are allowed to exist at all. And here's the really delightful part. When people first stumbled onto this problem, they didn't set out to explain life or matter or existence. They were just trying to understand why a tiny charged particle didn't behave the way it was supposed to behave. That's how discovery often works. You trip over a small inconsistency, and when you try to fix it, you discover that the universe is far stranger and more interesting than you ever imagined. Now, if you're feeling a little uneasy, that's because we've only cracked the door open. We've explained why atoms don't instantly collapse, but we haven't yet answered a deeper question that's been lurking in the background the whole time. Why do these particular rules exist at all? Why does nature insist on discrete states, on uncertainty, on this peculiar balance between confinement and freedom? And why do these rules seem perfectly tuned to produce a universe rich enough to contain complexity, time, and thought? Those questions don't live in a separate box labeled philosophy. They grow directly out of the same simple puzzle we started with. Why doesn't the electron fall into the nucleus? If you'd like, we can keep pulling on that thread and see where it leads. So let's keep going, but instead of diving straight into abstractions, let's play with something familiar. Suppose I hand you a rubber band and a marble. You stretch the rubber band between your fingers and let the marble rest in the middle. If you pull the marble to one side and let go, it oscillates back and forth. Nothing mysterious. Forces pull it in, inertia carries it past, and it sloshes around until friction drains the energy away. That's how we instinctively think the world works. Push, pull, motion, loss, end of story. Now imagine shrinking that rubber band and marble down to atomic size. The marble is the electron. The rubber band is the electric attraction of the nucleus. If you use your everyday intuition, the electron should oscillate, radiate energy, and eventually settle down right in the middle. Collapse. Dead atom. But that intuition comes from a world where position and motion are separate ideas. You can know where the marble is and how fast it's moving at the same time. Atoms don't play that game. Let me try a different picture. Imagine you're blindfolded and standing somewhere inside a large room. You're not allowed to stop moving, ever. If someone asks where you are, the best you can do is say, well, I'm probably somewhere around here. If they try to pin you down to an exact spot, you're forced to move faster. And if they insist on knowing exactly how fast you're moving, your position becomes more and more vague. This isn't clumsiness. It's not a limitation of your instruments. It's the rule of the game. That's what an electron is dealing with all the time. It cannot be both perfectly localized and perfectly calm. The more tightly it's confined near the nucleus, the more energetic and agitated it must become. And that agitation costs energy, so now you have a tug of war. On one side, the electric attraction is trying to pull the electron closer. On the other side, confinement itself is pushing back, demanding more energy the tighter you squeeze. The stable atom lives right in the middle of that argument. This is why the violin string picture is so useful. The string doesn't want to vibrate at a certain frequency. It simply can't vibrate at others. The geometry of the situation decides what's allowed. In the atom, the geometry of space and the rules of quantum behavior decide what kinds of electron patterns can exist. And those patterns aren't little circular paths. They're shapes, clouds, regions where the electron is more likely to be found if you go looking for it, and regions where it never shows up at all. Sometimes the shape is spherical. Sometimes it looks like two lobes with a gap in between. Sometimes it's a complicated flower-like structure that makes you wonder whether the universe has an artistic streak. But every one of these shapes is a solution to a very strict requirement: it must fit, it must be self-consistent, it must not bleed energy away into forbidden states. Here's something that often surprises people. The lowest energy state of an electron in an atom is not the one where it sits closest to the nucleus. It's the one where the balance between attraction and confinement is just right. Too close and the uncertainty-driven energy shoots up. Too far and the electric attraction weakens. The atom chooses neither extreme. It doesn't optimize comfort, it optimizes consistency. Now let's do a thought experiment. Suppose you try to cheat. You say, fine, I'll let the electron be fuzzy, but I'll still force it to spiral inward slowly, radiating energy bit by bit. Nature shakes its head. There is no allowed state slightly below the ground state. There is no gentle slope downward. There's a cliff. And once you're standing at the bottom, you can't descend further without violating the rules that define what an electron even is. This is not an engineering constraint. It's not a matter of insufficient power. It's logical impossibility baked into the structure of reality. And once you accept that, a lot of other mysteries start to loosen their grip. Why do atoms of different elements behave differently? Because the allowed electron patterns depend on the charge of the nucleus. Add more positive charge and the whole balance shifts. New patterns become possible. Old ones rearrange themselves. Chemistry is born not from arbitrary interactions, but from the bookkeeping of which quantum states are allowed to exist together. Why does matter resist compression? Because pushing atoms closer together forces electrons into states they are not allowed to occupy without paying enormous energy costs. Matter pushes back not because it's solid, but because it's constrained. Why do objects have size? Because the electron patterns that define atoms have size. You can't make them arbitrarily small without tearing apart the very states that give them identity. All of this comes from the same simple refusal of nature to permit certain combinations of certainty and energy. And here's a delicious irony. The thing that makes atoms stable is also the thing that makes them active. The electron is never at rest, even in the lowest energy state. There is motion, not motion along a path, but motion in possibility. A continual restless sampling of space. Atoms are alive with activity even when nothing seems to be happening. If you could somehow listen to an atom, it wouldn't be silent. It would hum with zero-point motion, with irreducible fluctuations that cannot be turned off. Absolute zero temperature does not mean absolute stillness. It means you've stripped away everything that can be removed, and what's left is still dancing. Now let's zoom out just a little. The same rules that stabilize atoms also stabilize molecules. When atoms bond, their electron patterns merge and reshape themselves into new allowed states. The bond isn't a hook or a glue. It's a shared solution to a quantum puzzle. The molecule exists because the combined system has lower allowed energy states than the separated pieces. Nature is always asking what configurations are permitted, and then calmly refusing to realize the ones that aren't. This way of thinking is profoundly different from the clockwork picture people often carry around in their heads. In that picture, the universe is a machine that runs because forces push things around. In the atomic picture, the universe is a system of constraints. Things exist and persist because alternatives are forbidden. And once you see that, you start to notice it everywhere. Stability doesn't come from rigidity. It comes from rule following. The atom doesn't need to be nailed together. It simply has no other way to be. Now, if this were the end of the story, it would already be strange and wonderful. But there's a deeper layer still, because these rules didn't drop from the sky as a random decree. They emerge from a more general structure, one that ties energy, time, and information together in a way that's both unsettling and oddly inevitable. We've seen how atoms survive. What we haven't yet faced is what that survival implies about the nature of reality itself, and why the universe seems to prefer this delicate, restless balance over all the simpler possibilities it could have chosen. That's where the puzzle really sharpens. Now let's slow down and look carefully at what we've really said, because there's a quiet trap hidden in it. We've been talking about electrons, energies, allowed states, patterns that fit and patterns that don't. All of that sounds reasonable until you ask a very simple question: allowed by what? It's tempting to imagine some cosmic rulebook, a list of permissions stamped a pipirovid or denied. But that picture is misleading. There is no external referee. The rules aren't imposed on the universe. They are the universe. To see what I mean, think about time for a moment. In everyday life, time feels like a smooth river flowing forward, carrying events along with it. But when you look closely at atomic behavior, time enters in a very peculiar way. Energy and time are not independent ideas. They're tied together. If a state has a very definite energy, it persists. If its energy is fuzzy, it flickers. This is why unstable atomic states decay. It's not that the atom decides to emit light, it's that a state with uncertain energy cannot last forever. The fuzziness leaks into time, and the system rearranges itself into something more definite. The ground state of the atom, the one that keeps the electron from falling in, has a sharply defined energy. And because of that, it doesn't decay. There's no internal clock ticking down to destruction. It just is. This connection between energy and persistence is one of those ideas that sounds abstract until you realize it governs everything you touch. Stability is not a static property, it's a temporal one. To exist for a long time, a thing must occupy a state that doesn't blur itself away in time. Atoms exist because they have found such states. Now let's confront another uncomfortable idea. When we say the electron is a wave, we don't mean it's a wave made of something. It's not waving through a medium like water or air. The wave is a mathematical object, a description of possibilities. It tells you what could happen if you interact with the electron. And here's the part people usually try to sweep under the rug before you look. The electron does not have a definite position, not hidden, not waiting to be discovered. It simply isn't there in the classical sense. What exists is a set of amplitudes, a spread of potential outcomes. And those amplitudes evolve smoothly and deterministically, following precise equations. There's nothing sloppy about it. The fuzziness isn't ignorance, it's structure. When the electron settles into an atomic state, what it's really doing is occupying a stable pattern of possibilities. That pattern doesn't radiate energy because there is no nearby pattern it can smoothly slide into. The math refuses. If you try to force it by disturbing the atom, you don't get a gradual change. You get a jump, a transition. Light is emitted or absorbed in discrete chunks. Not because nature is digital for fun, but because there are no in-between states available. This is where the classical picture truly breaks down. Classical systems change continuously. Quantum systems change by rearranging their allowed patterns. And now comes a subtle but crucial point. The same rules that forbid atomic collapse also forbid absolute precision. You can't build a universe where electrons sit neatly in place and behave politely. The very mechanism that grants stability also injects uncertainty. In other words, the universe pays for existence with ambiguity. If electrons could sit exactly at the lowest point of the electric attraction, atoms would be smaller. But then electrons would have zero uncertainty in position, which would require infinite uncertainty in momentum, which would require infinite energy. The atom would explode instead of collapsing. So nature compromises. It says you may exist, but you must spread out. You may persist, but you must fluctuate. This compromise is not optional. It's enforced at every scale where quantum rules apply. Now let's talk about forces again, because this is another place intuition leads us astray. We often say the nucleus pulls on the electron, but in the quantum description, what really happens is that the shape of the allowed patterns depends on the presence of the nucleus. Change the charge, and the landscape of possibilities reshapes itself. The electron isn't being yanked around through space. It's adjusting its pattern to the constraints it finds itself in. That's a very different way of thinking. Instead of objects moving through pre-existing space under the influence of forces, you have states reorganizing themselves under changing conditions. Motion becomes secondary. Structure comes first. This is one of the reasons why the atomic world resists simple visualization. We keep trying to imagine trajectories where there are none. The electron does not travel from one point to another between observations. It transitions between states. The in-between is not a story of motion, but of evolution in a space of possibilities. And now, if you're patient, this viewpoint starts to explain something even more astonishing. Why is matter solid? Why doesn't your hand pass through the table? The naive answer is electrons repel each other. But that's only half the truth. The deeper reason is that electrons are not allowed to pile into the same state. There is a strict accounting rule. One state, one electron, with only limited variations allowed. So when you push atoms together, you're not just fighting electric forces. You're trying to force electrons into states that are already occupied. The universe responds by demanding enormous energy. The resistance you feel is not mechanical, it's combinatorial. It's the cost of violating the allowed arrangements. Matter is rigid because the bookkeeping is strict, and this brings us back to atoms existing at all. The same principles that stabilize a single electron around a nucleus scale up into everything else. Periodic tables, chemical bonds, materials, stars. All of it emerges from which states are allowed and which are forbidden. Nothing in this picture relies on special pleading. There's no hidden mechanism that switches on just to save atoms from embarrassment. The rules are uniform and merciless. They apply everywhere all the time, That's why this discovery was so shocking when it first crystallized. It wasn't just a solution to a technical problem. It was a revelation that the universe is not built from objects obeying forces, but from patterns obeying constraints. Once you see that, you start to notice a quiet elegance behind what looks like chaos. Randomness appears not because the universe is sloppy, but because it refuses to specify outcomes until interaction forces its hand. Determinism lives in the evolution of possibilities, not in the outcomes themselves. And this has a strange emotional effect when you really absorb it. The stability of atoms is not a brute fact. It's a delicate balance that could have failed in countless ways. A slight change in the underlying relationships between uncertainty, energy, and interaction, and matter as we know it would be impossible. Yet here we are, in a universe where the rules land just right to allow structure without freezing it, motion without collapse, persistence without rigidity. The atom is not a thing, it's an agreement. A self-consistent arrangement that the universe permits to endure, and that raises a final, unsettling question that we can no longer avoid. If the existence of atoms depends on such abstract constraints, if matter itself is built from what is allowed rather than what is pushed, then what does that say about reality at large? About time, causality, and even the sense of continuity we experience as conscious beings? That question doesn't sit quietly. It demands to be followed. Let's follow it then all the way out without trying to tame it too quickly. If atoms exist because of allowed patterns, not tiny mechanical supports, then matter itself is less like a pile of bricks and more like a standing wave in the fabric of reality. And standing waves have a curious property: they exist in time, but they are not about time in the way moving objects are. They don't go anywhere. They persist. An atom is not something that happens and then moves on. It's something that keeps happening over and over in exactly the same self-consistent way. That's a very strange kind of existence. Think about a musical note held steady. The air molecules are flying around wildly, but the pattern stays the same. The note isn't a particular molecule. It's an arrangement that survives change. Atoms are like that, except the music is played by the universe itself, and the instrument is possibility. This is why atoms don't age. You can have a hydrogen atom that formed billions of years ago, and today it is exactly the same hydrogen atom in every meaningful sense. Not similar, identical. It hasn't worn down. It hasn't drifted. It hasn't accumulated damage. That's not because it's indestructible. It's because it's not a thing in the ordinary sense. It's a stable solution. Now let that sink in for a moment. The most basic building blocks of everything you know are not little pellets of substance. They are recurring answers to a question the universe asks itself: what configurations can exist without contradiction? And atoms are among the simplest, non-trivial answers. This reframes time in an interesting way. We usually think of time as the stage on which things happen, but in the atomic world, time is more like the condition that allows persistence to mean something. A state with definite energy does not change in time, except for an unobservable phase. Its existence is its endurance. Change happens only when states interact, when patterns overlap and rearrange themselves into new allowed patterns. Events are not driven by a ticking clock so much as by compatibility. This is why the idea of cause and effect starts to blur at small scales. An excited atom emits a photon not because time ran out, but because there exists a lower energy pattern it can transition into while satisfying all the constraints. The moment that path is open, the transition becomes possible. When it happens is a matter of probability, not scheduling. The universe does not keep a diary, it enforces consistency. And now we arrive at something that sounds philosophical but isn't optional. If matter is made of allowed states, then the distinction between real and possible is not as sharp as we pretend. Possibilities are not imaginary, they are the raw material from which reality is selected. Before an interaction, multiple futures coexist in a precise mathematical way. After the interaction, one of them becomes history. The atom doesn't care which one, as long as the bookkeeping balances. This is not mysticism, it's accounting. So why do atoms exist? Because the universe permits certain recurring patterns of possibility to endure. Why these patterns? Because they are the simplest ones that satisfy all the constraints simultaneously. They are not chosen, they survive. And once you accept that, something remarkable happens. The complexity of the world stops feeling like a miracle piled on top of a miracle. It starts to feel like a natural consequence of simple rules iterated relentlessly. Atoms form because they can. Molecules form because atoms can share states. Life forms because chemistry can build systems that maintain themselves far from equilibrium. Consciousness forms because some arrangements of matter can model themselves and their surroundings. At no point does the universe need to add a special ingredient labeled life or mind. It only needs to allow stable patterns to persist and interact. You, sitting here listening to this, are not an exception to the rules that keep atoms from collapsing. You are an elaborate extension of them. A vast, layered hierarchy of allowed states stacked on top of one another, all the way down to electrons refusing to fall into nuclei. That's a humbling thought, but also a comforting one. It means you are not fragile in the way a mechanical contraption is fragile. You are fragile in the way a melody is fragile. You persist as long as the pattern persists. And that brings us full circle. The reason atoms exist is not because the universe is sturdy. It's because the universe is constrained. It doesn't tolerate nonsense. It doesn't allow contradictions to hang around. Atoms are what happens when possibility finds a way to repeat itself without tearing the rules apart. So the next time someone tells you that everything is just atoms, remember how misleading that word just is. Atoms are not obvious, they are not inevitable. They are a triumph of consistency over chaos. And the fact that they exist at all is the quiet miracle that makes every other miracle possible.